Okay. If our phase interferogram we have we don't take into account for the topography effect, because probably we already know a digital terrain model, and we can remove from our measures the effect due to the topography surface of the Earth. We can analyze if there are some movement from the ground, from one image to another image, SAR image, if something is changed in terms of deformation, not in terms of noise scattering. So we speak about differential SAR interferometry. So in this sketch, we can introduce we speak about deformation, looking at if something is changed over time.
Okay.
Yes.
How the satellite is rotating? Is it rotating to look at the same place when it rotates again?
No, we are going to see in later how we collect data, but it's not looking just one place in the Earth. It's computing. You have different type of mode to collect data, in a strip mode data, or you can have a spotlight mode, and so on. We are going to see later when I show you some satellite mission, and I describe this. But the most used mode is a strip mode. You are going to cover the Earth by strip, and the other is rotating under the satellite.
So you different places.
Yes, different places. Yes, due to the rotation they have.
To compare whether a place deformed or not, whether there is a change in or not, we have to look at the same place at different epoch.
Yes.
Okay.
Yes.
Okay.
We are going to compare. Yes,
yes, so we have the same satellites passing twice above a certain region?
Usually we have two satellites.
Okay.
Yes, that pass at different time. There is an interval between one satellite, a time interval, one satellite and another satellite. This to give the SAR images, the InSAR. And after, if we compare two InSAR, so two different interferograms take a different time, we can have the differential inference SAR.
But can atmospheric conditions change from one passage to the other?
Yes, but I already removed this from this part, more or less. When you compute images, or you are going to, yes, when you compute this pair of images, you are going to take into account also for this.
I thought it was a result of the InSAR reduction.
Yes. So, this is another plot of this company. It's an important company in Europe. It was a spin-off of my old university. So you have, for instance, you have an antenna on a zone, and this zone is under deformation or subduction. So you have this acquisition at time T1 and this acquisition at time T2. So the difference is in the range is due to this deformation. It's not due to different position of the satellite, for instance. So we want to correlate these differences with our phase to see the differences. So we have to introduce to note an important thing, that when you are looking at the ground, you are looking the ground along the land range. This is called along the line of sight. So you are doing all the measures that we are describing are along this line of sight. And so to be honest, InSAR measures just 1D displacement along this line of sight. And after we can try to project this deformation, this change in the distance in other reference, in other coordinates that are more used for our application. But what we see are deformation along the line of sight. This is important, and often in the paper you find this specification, and you find this LOS. Okay, so it means that, for instance, this is the real vector of deformation. This was a point that moved to this point. So we see this along the line of sight. So we see this as a projection of this vector along this direction. And if you are in this condition, the change in this direction in the line of sight is smaller than the real one. So the amplitude is just a projection. So it depends on the direction of the real deformation. This is really on is the most horizontal deformation. So when you project, even if a big deformation along the line of sight, you see a small deformation. So often this quantity is not well determined. But if you have a deformation really vertical or very close to the vertical line, so using projecting this along the line of sight, you can see quite a lot of this deformation. So often in the paper you say that the authors describe the deformation along the line of sight. So when you use this information, you have to be careful. It's along this direction, not along the vertical as we think. I think it depends on the look angle. And often we have also, I think that we have no. So, okay, this is important. The precision estimation of the true vertical motion and east-west component of the motion increased by using ascending and descending data. Also in this case is the fact that we are observing the Earth with two different geometry, with the satellite going from south to north or north to south, help us to really find find the most the vertical deformation of the point. For instance, this is real. We have the projection, and combining this, we can have more information. Okay, just as a plot. And usually the SAR is used. Okay. What do we say, SAR with respect to GPS? GPS give you information on the 3 dimension, but usually we use GPS, especially in the past, for deformation just in horizontal coordinates, because the height was affected by many errors. Now with this very long continuous GPS time series, we started to use really also the vertical component of the data, because we have very long time series. Even if this time series are noisy, noisier than the planimetric time series, now we can use this with a good accuracy. So with the GPS we have continuous data in the times, a result every day, but a most precise precision in the planimetric component. With SAR, we used to say we have a very high spatial coverage, because we are speaking about images, not single point. But we don't have a high time signal resolution, because we are going to see that, for instance, for S1 we can have an image for this type of application, the InSAR, after 1 month. So is just a sampling of the movement. Now we have reduced this time interval between one InSAR images to another InSAR images. Sentinel-1 have a time span of 13 days. And okay, InSAR is used especially for vertical deformation instead of the GPS that we use for horizontal deformation. So it looks like complementary techniques. It's not really true, because we have seen that with the GPS we can have information to the vertical, and also with SAR. At least in one direction, east-west, we have information. Northeast, no, because if you project, and because the satellite is moving north to east, you don't have information in that direction, in the direction north to south. But we have also information for the horizontal. So I think that are two techniques that have been used together and try to find the best information that you can from GPS and the best information that you can have by SAR. And often I think that can be combined, not just to reduce some atmospheric data and so on, but just put together some instrument. We are going to see that we can put some instrument called corner reflector that are special reflectors that increase the scattering, the signal coming from a point of the Earth. So putting this instrument close to the GPS antenna help us to geolocalize your picture, because it's difficult to geolocalize a picture SAR image. You are sure that we are speaking about the same pixel, the same zone. Okay, this is some note. To separate, we have to, from this part, to measure deformation, we have to separate the topographic signal due to the topographic surface of the Earth. And to do this, it's important to use baseline that are small enough. This is the formula, and this is the formula that gives us the phase related to the topographic surface of the Earth. If we use short baselines, this part became shorter, you can see from the formula. So if you use baseline short enough, you can reduce this effect. And you can use also a digital terrain model available, and it's not necessary to have a very high precise digital terrain model, because when you are using the same model in one interferogram and another one interferogram. So when you combine, you can, if you have some biases related to the digital terrain model are constant, so you can remove. It's just an approximated model that help you to reduce for this one. And otherwise, you can improve the number of InSAR that you are going to combine to remove this part due to the topographic surface. Okay, this is some application. You already well know this was the first one when you have a plot of an earthquake, and it was in 1993, and using SAR images, they obtain the displacement field due to this earthquake, the landers in the United States earthquake. It was the first time. In this picture we can see that this is what they have seen by the SAR, and it was predicted by a dislocation model of the fault. We can see very similar patterns. So it was the first time that it's a laboratory test where you can prove your equation or your dislocation model. But I know that you find now we are full of this type of examples, because now when an earthquake occurs, we are waiting for to see the SAR, the InSAR product, to see really all the deformation of the area. We already know. Okay, and this they was lucky to obtain this figure because they are in a good condition. They can remove the scattering noise and so on. So they was able to obtain a good images. For instance, few months later, in this earthquake in India, they was not able to have these good images. I think that because this part of the earth was really covered by vegetation, so probably they have problem in the reduction of the data in that time. Now we have also increased our software, our algorithm and so on. But in the past we was at the beginning. This is another earthquake in Turkey. Okay, just to say you can see in the picture, this is to say in the picture when you have this type of picture with SAR result, they put the fly direction and they put the line of sight. So this information you have every time to check when you are going to see what you are a SAR result, and often you have to know this. If this is the deformation of along the line of sight. So if you want to compare with your model, you have to put in the same frame. So in the same, or you project your result, your model along the line of sight, or you project the SAR image in the reference that you're using for instance, this location model. It's important. This is due to the L'Aquila earthquake in 2009 in Italy, and you can see that there are part of the parts that are more solved, and other one are not so well solved. And another example is the Ettermine earthquake. We talked yesterday about this earthquake. Was the one used also for the principal component analysis. They found in paper the effect of this earthquake in a station far from the epicenter, and they found this using principal component analysis with the GPS. Each color cycle represents, it's important to know the scale, 10 centimeter along the line of sign. And you have, so when you go from yellow, red, blue, and you start again yellow, red, blue, it means that you have to add 10 centimeter. And this is a deformation, another example in African rift, and it's a deformation related to volcanoes.
Excuse me.
Yes.
From the slide, can we understand somehow from the picture that in the first case we are in a descending geometry, while in the second we are in an ascending? No, I think that from the people have to give you this information. You have to put this label. So this is to say when you have a picture like this, you have information from one direction, this direction, and you can see that you are not seeing the same result, exactly the same result. So it's not so easy sometimes to interpret in a way exactly the result, and probably it depends really by the geometry, by the fault, the direction of the deformation, and so on. Is it possible to use these results very close to the epicenter? Because it seems that there is a sort of decay of the signal.
To have a zoom in.
Yeah, I mean to be able to count the fringes, for example.
Yes.
The fringes near the epicenter are not clear.
because often the things are destroyed, so you really change. If you are in a city and you want to see the often you have a lot of deformation, a lot of destruction in close to the epicenter. So if you think, for instance, L'Aquila, that the city was destroyed, so it's difficult to find the same reflector that give you the image to correlate the images. It's better how far. What? Sorry?
We have an incoherent signal.
Yes, because if you use these corners of the roof, give you a very strong reflection signal, and after for the earthquake, the main shock was destroyed. You cannot find more this information in the other InSAR images. So in this part, it's very difficult to have occurrences. It depends when yes, I think the aftermath was not in, so I don't know, I'm not sure, but I think that was in a very, not in a city. It's not happen in a zone with a lot of industrial or houses for man. So in fact, in the L'Aquila was really more complicated. Even if, no, probably the magnitude is not so different. No, it was very bigger. No, sorry, it was bigger. But we have a lower magnitude, but this part is really covered by building and also by vegetation, because there's a part in the Apennines mountains in Italy, so there is a lot of vegetation. And also for the Emilia, no, but this probably was a problem of coverage of the images, not a problem of this.
Here, the image here, I think we can know the line of sight and the direction of the satellite from this image, ascending and descending. Ascending means when the satellite goes from south pole to north pole.
Yes.
And descending from north
to south, yes.
So I think the satellite radiates at
yes,
left side or
right side, yes.
Right. So from this information we can know which is the line of sight from this information. It's enough information to.
I was also able to read this type of image, so I'm not sure that I was able to distinguish which is an ascending and descending images, but usually you find this information, so you don't have to interpret it if it was an ascending or descending, but probably people that purchase such data can understand if one, because it's true, it depends if you look at the Earth by the right side or on the left side during your observation. This is from have you got any other question? You look really interested. You touch the physics, geophysics. And these are for the volcano eruption, and okay, you have a deformation along the time of these volcanoes, but it's very small. Just to say, we can also use not just for faults, but also for volcano deformation. And this type of application is also used for building control. There is some colleagues, was a former colleague of Polytechnic of Milan. His work in Barcelona in Spain, and he wrote writing a lot of paper about the monitoring of building or engineering infrastructure using SAR. There is a lot of application. In the city it's quite easy. If a building destroyed, collapsed, and you have sufficient images, you can really see this deformation of the building, because you have a strong refraction from this type of building. GPS time. Okay, now the people have collected a big number of images, of InSAR images. So InSAR, I remember, is a combination of two SAR images. So we have a lot of this information. Now, so we started to speak about the InSAR time series. I think, I talked about this problem 2-3 years ago with some researchers visiting associate professor of ICTP of this problem, and I realized that I think probably the things are changing, that we have a lot of things to do in this field, because okay, with the GPS it's simple. We have a continuous time series. It's clear the stations that you are looking for and so on. With the SAR image, what is a time series of images? Okay, we can see the differences, but we need to compute this deformation. So it's not so easy. Sometimes we fix a point and we are going to see this point along all the InSAR images and produce this time series. But our sample time series, not continuous like in GPS. So I think that in this field, probably we have to improve our knowledge in how to deal with the huge quantity of data, with the spatial coverage of data, but not continuous in the time. This is my opinion, but I'd like to work on this field when I've got time. So when you have to produce the InSAR, you have different approach. One is the Persistent scatter method, that was the first one. Another one is called small baseline method. So persistent or permanent scatter is based on the consideration that we have done talking now, that in some point we have a very low temporal and geometrical decorrelations. Means that some point on the hair can give us very information with good power. I can see every time this pixel in my the contribute of a point on the earth is I in the pixel that we are going to see, because I have a surface that reflects in a good way the signal coming from the satellite. So this is called permanent scatter. So it means that I have a low temporal decorrelation. The object don't move. The objects don't move or change shape over time. A geometrical decorrelation. Okay, they produce a good signal. Also, if you change your looking angle, the geometry of your observation, and this is general. Object like building or in general is structure. Okay, so building are quite a good reflector. Also this metal things, pylon, and so on. There is something that gives us a constant signal when you observe with your SAR. You obtain every time a good signal from this object. So they are very important in the definition of your pixel. Give us a stronger effect. So if you have pointers that don't give you a stronger effect, so you have a more scatter images.
But we have, if you have a point that give you a strong answer, you have a more clear acquisition. The definition of that pixel is more clear because as you have a dominant part. Okay. And for instance, in this case, these are time measure. You can see that you don't have continuity. So often you compute the total deformation like the sum of the deformation between one InSAR to another InSAR figure. We don't have continuity, so it's like step function, more or less. For this reason, I think that now that we have a more continuous acquisition, probably we can find something more precise, more detailed. We can also use artificial reflector. Artificial reflector are surfaces that have a radar cross section. We have seen this quantity in one of my first equation at the beginning of the SAR. We have seen the formula between the radiation that was sent by the satellite and the radiation that we received from the ground. One of the variables on this equation was probably the first formula in the SAR lesson. There was this quantity, radar cross section, that is measures the effective that give you a measure of the signal that you can have back and the energy of this signal. So this is from a study that I've been done with my former university, and they studied different corner reflector, artificial corner reflectors, means special instrument to put on the ground and to increase the signals that arrive from this. So to better define the pixel, like in the previous picture. This was an experiment on a roof of a laboratory in Milan, and we put here a GPS. Now you cannot see the antenna, and these two corner reflector with different orientation, because one was for the ascending, the other one for the descending orbit, to maximize this. And using this frame construction, we first we apply some movement, changing the position of this corner reflector, and we recorded, we measured this using GPS and SAR. It was because a company asked us what is the precision of this monitoring. I can use this for monitoring, for instance, some dam or some very important structure, and so building and so on. And what we obtain are very precise definition, also with the GPS, but with the SAR, but also with the GPS. Of course, it was a very we are working in a very optimistic way. We have 2 points. We are going to record the formation of a point with respect to another point, and these 2 points are really close. So, for this atmospheric effect will cancel by itself because we are looking very close point and so on. But okay, it was interesting. Just to say, now this was a huge, big corner reflector. I see now that there are shorter corner reflector, and I see that when we put a GPS time series, station, if you have enough money, I don't know the cost of this instrument, could be interesting putting also this type of corner reflector. I don't know if the
if you have to check well this instrument to remove water on snow sometime. I don't know how lasting the time, but I think it will be really interesting. So we have really the same information. We are sure that we are seeing the same pixels that are seen. Pixel means the same ground of the GPS. So we really connected the two observations. Also to be sure, because in the SAR we have a relative. This is important. We have a relative deformation. When you look at SAR, you don't have absolute deformation. In GPS we have absolute deformation with respect to our reference frame. We say it's moving of 3 centimeters, not with respect to what? In our reference frame. In the SAR, in the picture, we started to count for the fringes, but we started from a point, and the people decide, okay, this is a stable point, and I'm starting from this point to count the deformation. So we decide which is our reference point. So it's a relative measure. So if you are sure that that point is close to a GPS, you can connect this, have all the information by the GPS. So you can say it's a really stable point or it's also moving. I can know by the GPS, for instance. So I think that we have really to invest in this type of instrument connected to the GPS. Or there are other techniques. This is also from this TNE company. It's a private company. You have to pay the service for the company, but was one of the most important. The first one that using the permanent scatter shows the best result on using SAR. So, and they have a clear website when you find a lot of plot, and I use this one. Oh, another approach that was the approach used by the associate professors that sometimes comes to ICTP, according with ICTP, is the small baseline method. The key point is the coherence. In the other approach, we are going to show where we have the stronger signal, so stable points give us stronger signal. In this case, we want to maximize the coherence. In this case, we can use a small orbit separation. We try to minimize the baseline, the distance between one acquisition to another acquisition when we are going to build your images, and a short time interval between one acquisition to another acquisition. So you have. If these are your acquisition, you can over the time, and this is the perpendicular, the dimension of the perpendicular baseline. You have different approach how you can connect this to, for instance, to this first image. You can compute all the baselines with respect to the first one, or you can connect the image to have a small baseline and so on. Or you can have a consecutive, so reducing the time between one image to another image. Are different approaches in processing data, in processing InSAR data. To produce InSAR, from SAR to produce InSAR, and often have information for InSAR. Okay. Yes. Now this part is finished. I just give you an idea of the. Okay, I'm not an expert on SAR. I'm going to show you, to give you basic information. to be able to read the paper about SAR. If you are interested in SAR data processing, I invited you to contact our associate researcher or professor, or find something that really touches this data. Now it became more easy because there are a lot of software available. If you look at also UNAFCO website, we have already talked about UNAFCO. If I remember, there is some free software that you can use. Also for the images, up to some years ago, you have to buy these images, and quite expensive. So it was not so easy to do research inside because it was really expensive, these images. Now is, for instance, with Sentinel-1 mission that we are going to see, we have free images, so you can really use it also for research, even if you cannot invest money on this, on buying data. So this is really important. So this is to give you an idea why when you read the paper on SAR, you see ascending, descending orbit, line of sight, what is mean, and the problems that we can have. Is just to have an introduction. This was the aim of this part of the course. Okay. Now we see the last part is just having some information we have at the end of the course, and someone also to ask about the exam. So I try to have time to speak about also the final exam. So probably this plot is not updated because okay, now. But just to say you that we started with the first mission was Earth-1, after we have Earth-2 by the European Space Agency, and RadarSat, other mission, and ENVISAT. We also have some gaps in the middle. In some period we don't have so many data images to be processed for this type of application. We have quite a gap. And now in this, you can see that in the last 10 years we really increase the number of observation of the Earth using radar system. So we have this important mission, but we have to pay to have these images. It's provided by Italian Space Agency. And now from, no, I think that they started to not in this year, but in 2014, we started to have data from the Sentinel-1 mission, and so on. So we are increasing the number of information that we can obtain by radar. The different agencies in the world, space agency, spend money to provide this type of measure.
Is there also one called Cryosat?
Cryosat, yes, but because, okay, we are going to see, if you want to perform measure on the land, it's different that you want to perform measure on the ice or on the water. You have to is an instrument differences between the signals that you are going to use. Cryosat, yes, is a performance for the study of the ice, yes. Now we are talking about especially mission for the land, not covered by ice. Okay. There is a lot of, also yesterday I read a paper that the Italian Space Agency put in orbit a new multispectral instrument. Was a test, will go in a month, this satellite with a very instrument will multispectrum. Multispectrum means that we can use obtain information, for instance, infrared or near infrared in different wavelengths, not just in microwave. And this is important to have a lot in many fields, to have a thematic map or other type of information for temperature, for the content of water of this ground, and so on. Really important, and this is really increasing the number of this type of mission. This okay, probably I have to update this with putting also Sentinel-1 and so on. This is old, but to say that with the time that we improve the repetition, we are using multipass system, so we need to compute inside image. We need SAR image collected into different time. So with the time we reduce this type of interval between one image to another image. So we have more continuity over time. And this is the band of the signal. Often we use C-band. So C-band are 6 centimeters of wavelength. And this is the polarization of the signal. It's important, the polarization, especially multipolarization, allows us to, as Enrico told, to perform different type of measure with respect different surface. And okay, this is the agency, European Space Agency, Canadian, Italian, German, and so on. It's not important. Okay, also this, I think that is not so important, some technical information, but for all the satellite. Shuttle miss. Okay, what is important here is more or less the altitude. This is the altitude of the satellite, so more or less between 600-700 kilometers above the Earth, more or less is the resolution of the SWOT area. SWOT area was the resolution in the ground land range, the projection of the land range of the ground. You can find that we have for CSAD 25 meters and so on, but more or less it's the same. And oh, sorry, the resolution. This is the SWOT area. The resolution cell is more or less the same, about 25-30 meters. This is important. It was one of your question. Some SAR systems can operate in different imaging modes. So how they collect data? You see that they are moving, they are send the electromagnetic wave in the slant range. But how can we cover the hertz? We produce the image. There are different methods. The most used is this one, the strip map mode. So it's moving, for instance, south to north, look in this direction on the right side, and it produces this type of strip mode, a strip along the path. Or we can have also this type of moving, spotlight mode or scan SAR mode. Sometimes are called also in different ways, but to have an idea. Okay. This is the most used method, and so they have a limited SWOT. They design the width of the SWOT and produce these narrow SWOT. And target point with different distances perpendicular to the flight direction of the radar can be distinguished. Okay, this is the standard way to collect the data. Okay, another mode is a scan mode. Is okay, they can steer the antenna, the system that send the electromagnetic wave, changes this angle so they can cover more part, a bigger swath area. And another application, the spotlight. So you force your system to illuminate more or less even often the same position of the Earth, the same area or different area, but you select to look, really look for a long time the same area as you can, of course, during the flying. And so in this case you see the same part of the hair from a different point of view. And this is important because you can can have more information and process the data in a best way. But you have a very high resolution, but just in a few areas. You have a lot of information, but for a limited area. So it's this is a standard way. It's like a medium average observation way. We have a medium resolution of what you are going to see. If you need to have more information but faster, you can use this method. You lose in terms of precision of what you are going to see, but you cover a big part of the Earth, of the ground.
So
Yeah.
there we can see what on the previous slide, the two strips. So
Yeah.
the first one, the previous one is the
Is
strip
it-
covered by the same satellite.
This one, yes, because the Earth is yes.
So there can be a gap between the two strips. Or it's just a picture.
I don't know this.
No, it's just curiosity.
Probably you can add some gaps and you are going to fill a few days later, so probably. But I'm not sure about this. I think that you can. In fact, when we have at the earthquake in Emilia-Romagna, the first picture was of the co-seismic, was just a part of the zone because they don't have images. But in the weeks later, we have also the other part. So probably we can have some. It depends on the area that you seen. In this part was a quite wide area that you want to check for this earthquake, so probably it was not covered in one strip. But I'm not sure. I have to ask for this information because okay, when an earthquake happens, what's happened? You are looking for the last image that you have and the first image. The last image that you have before the main shock, and the first image that you have. You don't fix the time. Probably one image could be 3 weeks in the past, 3 weeks before the earthquake. The other image could be 1 day after the earthquake. It depends when the main shock happened. So probably you can have some gap, but the system is made that you feel all. Probably you go in the same place after 1 month, but we have to check the period of the orbit to be sure about the answer, because it's a combination of this and the rotation. But probably to go again on the same place of the Earth, for instance for Earth 1 we have to wait from a month, but for a zone close probably the satellite is already passed. Okay, I think that they have not. Do you understand what I mean? Yes. more or less.
I was curious, why the...
These are some examples of missions of satellites that you can use. This for the German agency, if I remember, that some instrument we can select the operation mode. You can say, okay, I need that you work in a spotlight mode, in a strip map mode, in a scanner mode, and so on. You can decide. And also Cosmos SkyMet, constellation of small satellites for Mediterranean basin observation. Was for the Italian Space Agency and was set up with 4 satellites, but you have to buy to pay to have these images. But it's important because it's very good for this type of observation in this area. And we have spotlight, strip map, or ScanSAR mode. You can decide. Okay. I want to explain better what was a shuttle radar topography mission by the NASA and NGA. And it was a strange satellite with a long baseline, an antenna of 60 meters. And you have an antenna here, that the green one that transmits your signal, and your signal reflected has been measured by an antenna below the satellite and antenna on the end of this baseline. Okay, so you have 2 SAR images collected by this antenna. No, yes. You collect data by this antenna and this antenna. So you have a baseline fix and a single pass. Do you remember when I say I can have produce InSAR, I can combine 2 InSAR images. One is the only one application with single pass mode. And they cover the 80% of the land, and apart from the pole zone, Arctic, Antarctic zone, and they perform all this type of measure in 11 days. Just 11 days cover all the world, apart from the north and southern part, with a resolution of 30 for 30 meters. At the beginning, they will give us just this type of product with sub resolution, with 90 per 90 resolution. I don't remember if that now they give. I checked this since a few weeks ago, and probably now they give also the higher resolution, but I have to check. And the precision in the height is 60 meters. It means that in some part is 60 meters, in other part is better. It depends. 60 meters is could see for you not a good resolution, but in many applications it's really sufficient, this type of precision. And all the height are given in WGS 84. This is the comparison between the digital terrain model produced by SRTM and another available digital terrain model, GTOPO 30, sorry. And you can see that you really improve the quality, the resolution of the knowledge of the ground, so it's important. I don't know which part of the world it is, but you can now really see the mountains, all the quantity. And okay, these are some references, but okay, I put. I want to put at the end, because yesterday I introduced, sorry, not yet. In the last day I introduced also a slide on Sentinel-1, because now is the most used mission for SAR data. So I'm going, and okay, this is the references, but yesterday when I checked some information, I found also this document by the ESA website, and I find this presentation really clear with a lot of information. It's quite big, more than 250, if I remember, number of slides, but I found a lot of information, so that is a very good starting point to see the SAR. Otherwise, there are in this book there is really for the first one, and you can find all the equation for the data transmission, electronic part of the SAR, and so on. This was a PhD thesis, very easy, and okay, as a book. The website is full of information, especially for your academic website. Okay, Sentinel-1 is important. The European Space Agency has planned to put in orbit 5 missions. Sentinel-1, 2, 3, 4, and 5 for the Earth observation. Is part of a big program, Copernicus, that want to increase the Earth observation. And the first mission, Sentinel-1, is composed by 2 satellites and have an orbit period of 12 days. And it's important that I would think is to the question of Vico. I'm going to check and give you. Okay. And okay, what I want to say it's important because in the other mission they put other type of instrument, multispectral instrument for hazard, for agriculture, and so on. In the first mission we have SAR instrument. They've chosen to use a C-band as the signal to have a continuity with the previous mission, X1 and ISAT and so on, where they're using C-band. So we can really combining also this product, also data from the previous mission. They use 2 polar orbiting satellite and so on. Okay. Also, this type of, okay, the strip mode is the most used, the standard mode to perform a measurement, but they can also use other type of observation, what we call waves that we have called spotlight, or extra wide swaths that we have called scan swaths, and so on. More or less the concepts are like what we have presented before. And the resolution, we arrive to 5 per 5 meters, so we really increase the resolution. If you use extra wide swaths, for instance, you reduce the resolution, the dimension of the resolution cell. And this is the swath width. Now, probably the velocity is being set to be sure to cover all the hertz, I think, without gap. Yes. In fact, if you see this swath width, it's quite big. But I'm going to check. These are all the polarization of the signals that we can use. H is for horizontal, V for vertical, so all the combination. We don't speak a lot about polarization, but when you perform a measure with this type of instrument, one information, when you measure the phase is also the type of polarization of the signals that you are going to receive, and from this you can obtain different results. So have you seen, this is just a project on the Italy, what is mean working with extra wide was mode or strip mode and so on. Okay, see, because I think that okay, I don't see nothing. I'm going to check this step. And in this plot that I found in the ISA there is a number, okay, 12 days is a day of orbit, but you can also have more dense information, but I'm not going to discuss a lot of this figure because I'm not sure. You can see, just to say that in the Arctic part we have less information. And so this is the result for Sentinel-1. Was for the earthquake in central Italy in 2016, and this is the result of this analysis. We have, or you remember, to understand this type of plot, you have to know at which distances correspond each franges. So in this case was 3 centimeters of motion in the line of sign. And okay, I cancel if you are in ascending, descending orbit, or this is a combination. Probably there is this information in this part. And okay, the Sentinel-2 is different. They put on board a multispectral instrument, but okay, I finished this part.